All right, so this is the last bit that we're going to look at in analytic geometry, and we're going to look at ellipses, and we start, just like we did with the other ones, with just a geometric definition. So constructing an ellipse is actually easy. What you do is, imagine you have you have a board, and you have a couple tacks. You put your tacks at these 2 points, so those are fixed points. Each of those points is called a focus. They are collectively the foci of the ellipse. And then tie a string to either end, right? And give it slack, so it's just loose. And then take your pencil, pull it so it's tight, and then move it all the way around. And that's how you make an ellipse. So the definition of an ellipse is just that it's the set of all, so you fix those 2 points, and it's the set of all points for which the sum of the distances, so here d1 plus d2, is the same. And you can just sort of construct it with that string and a couple of thumbtacks. We're going to look first at ellipses that have a center at the origin. And the one we're looking at here is sort of oriented horizontally. And if it's oriented horizontally, it will have this basic equation with the center at the ellipse. And in fact, it even still has this basic equation, even if it's oriented vertically. It just, depending on which one of these numbers is bigger, will affect how we can tell whether it's oriented horizontally or vertically. So suppose we have this ellipse. So I've marked those foci and those coordinates at C0 and negative C0. The ends here, on the long way, like this point here, we'll say that's at A0. And here's negative A0. These guys are called vertices. So each is a vertex. The points on the other ends aren't really given a special name, but these points are 0, B, and 0, negative B. That is not at all a coincidence that this A and the B, as I mark them here, are the values of A and B as they appear in this equation. So if I'm looking at an equation like this, if I have it in this standard form, I know where the vertices are and where the ends of what we call the minor axis. So an ellipse has 2 axes of symmetry. The long ellipse is called, the long axis is called the major axis, and the short axis is called the minor axis. So those points at the top and the bottom, the 0b and the 0 minus b, we just call them ends of the minor axis. They don't have a special name. But this is the major axis. And this is the minor axis. Now we're not going to derive this standard, the standard form of this equation like we did with the parabola, but you certainly could, and I think it might be. Oh, it's not in our Larson text. I could post something that kind of shows that derivation, but what we are going to derive is a really important relationship between the values of A, B, and C. So first, we know what makes something a point on the ellipse if the sum of the distances between that point and the 2 foci is always the same, right? So let's examine a point. Let's find D1 plus D2 for the point A0. And so this point right here. Now the sum of the distances, so D1 is the distance to this focus here, but that's a horizontal distance. The way we get a horizontal distance is just right minus left. So A minus a negative C is A plus C. And the distance to C0, again, right minus left, is A minus C. And so if we add these up, we get 2A. What makes something a point on the ellipse is that the sum of the distances never changes. So I actually know that regardless of any point that I pick, the sum of the distances is going to be equal to 2A. Let's do this again. But now we're going to pick an end of the minor. Let's pick this point up here at the top. So distance to negative C, 0, and distance to C, 0. All right. This, I think we could do without too much work. It's not quite as simple as just a horizontal distance, but what we want is, here's D1, is that distance right there. And we can, we could use the distance formula if you want, or we could just sort of rely on Pythagoras more directly and look at this right triangle. I mean, that's what the distance formula does anyway. But this distance here is C, right? Like it's from the origin to this point, negative C, 0. So that has distance C. This distance here is B. So this distance here is going to be, what, the square root of B squared plus C squared? And if we go up here again to the figure, if I want the distance to the other focus, what is that going to be? Same thing, right? I mean, it's just the same triangle, but it's just sort of reflected across that axis.
Using square and negative.
Yeah, yep. So is also the square root of B squared plus C squared. So that means that no matter what point I pick, oh, we haven't added, I didn't add them yet. If we add these, so D1 plus D2 is equal to, if I add those together, I'm just going to have 2 times the square root of B squared plus C squared. So that means that no matter what point I pick, if I add up the distances to the two foci, we're going to get that as the sum of the distances. But we already found that the sum of the distances was equal to 2A. But these have to be the same, right? That sum of the distances is fixed. That's what makes this an ellipse. So that gives us this equation. 2 times the square root of B squared plus C squared is equal to 2A. Let's divide out that 2. And I'll get rid of the radical. So we could square both sides. And we get B squared plus C squared equals A squared. It looks like a kind of perversion of Pythagorean theorem, because we're used to thinking of C as always being the longest side. But this is true. This is a relationship that holds true for any ellipse. Now, in this ellipse that we were looking at, so this is true for all ellipses. In the ellipse that we've been working with, the center is at the origin, right? So A, B, and C were those coordinates of the vertices and the ends of the minor and the foci. Now, so in a sense, we might think, okay, well, this is true as long as our ellipse is centered at the origin. It's actually true for every single ellipse as long as we understand that the values A, B, and C if they simply represent a distance from the center to each vertex, from the center to the foci, from the center to the ends of the minor. Okay, so this fact is useful. It's not that we need to use it for every problem we solve, but it comes up often enough that it's one of my kind of go-to facts if I'm kind of stuck or not sure what to do and I'm working out an ellipse problem, like, you know, that might come in handy. And it is something that we should know. If our ellipse is centered at the origin and is oriented vertically, again, the vertices now are going to be at the top and the bottom. We'll still let A denote the distance, so it's 0A and 0 negative A, and then the ends of the minor at B0 negative B0, and the foci are always on the major axis, right? The foci and the vertices are all on the same axis. And it has the same basic equation, right? This looks exactly the same. The only difference is, in this case, a squared is underneath the y squared. Now, when we look at the equation that we just derived here, that relationship between a, b, and c, and geometrically this fact is going to make sense, but a, b, and c, which one has to have the biggest value? A, right? It's like, you know, it's like saying we could draw a right triangle and where a is the hypotenuse, so that has to be the biggest. And we could also see that visually up here. Certainly A is bigger than B, and A is bigger than C because it overshoots the focus. So we can tell which way our ellipse is oriented. If we have it written in standard form, we could tell which way it's oriented because A is always bigger, so I just look to see which has the biggest number underneath. Let's do an example. Let's sketch this curve. They've given us the equation of an ellipse in standard form. Which way is this oriented? And how do we tell?
Horizontally.
Yep.
Because of bigger numbers under X.
Yeah, yep. So that means that the major axis is the x-axis because it's oriented horizontally. And then we want to find the vertices and foci. So how would I get the vertices? Like,
You gotta get it in the formula to find C.
well, that's what we'll do to find the foci. Yeah, but the vertices. What value corresponds to the vertices?
Negative A.
Yeah, right. So that's the value. If I know what A is, then I pretty much get the vertices almost for free. And so in this case, A squared is 25. So A is 5. And that means since the center is at the origin and it's oriented horizontally, that means that the vertices are at 5, 0, and negative 5, 0. They didn't ask us to find the ends of the minor, but I'm going to find them anyway because they want us to sketch it, and that's pretty useful to have. How do we get the ends of the minor? Like, what's the value that we're looking for?
That's a
B.
B, right, yep. So I know that B squared is 9, which means B is equal to 3. And so the ends of the minor are at 0, 3, and 0, negative 3. And then what do we do to get the foci?
Find C.
Yeah. Yep. So we can use that equation that we derived, right? We know that b squared plus c squared is equal to a squared. So that means c squared is equal to a squared minus b squared, which is 25 minus 9, or 16. And so c is equal to 4. And again, the center's at the origin, so it's just 4 units out from the origin. The coordinates of the foci will be 4, 0, negative 4, 0, because it's oriented horizontally. So we provided the information they asked for. They wanted the vertices and the foci, but they also asked us to sketch it. So let's go ahead and do that. And then I just do my best to sketch. There we go. Are there questions on that example? Okay. All right. So, yeah, go ahead.
I'm sorry, the foci is just making it the right triangle, dropping it down from the vertex. Or I mean, from the, I don't know how I'm saying it, but it's the right triangle.
Well, yeah, I
It's
mean,
just kind of,
so here are the foci here, right? And you could, I mean, if you drew this right triangle, you know, like this hypotenuse would have length A, not
Right.
the same as that length.
I'm just wondering like what the other purposes of the foci are.
Oh, that's just how we define, like, if you want to make an ellipse, you have to start with 2 foci, right? And then what makes something a point on the ellipse, like if I pick whatever point, let's say I'm here, right? What makes it on the ellipse is that if I take that distance and add it to that distance, that's going to be fixed no matter what point I pick. The sum of those distances will always be the same. So like when I was talking about like if we wanted to construct it physically, I say, oh, okay, these 2 foci, let's put some thumbtacks there and like let a string hang like kind of slack, and then just pull it tight and like move it all the way around while it's tight. And like that's what an ellipse is. So you need the foci to make it, right? The equation of an ellipse, this standard form, one thing that's pretty important about it, if it's in standard form, it's got to be set equal to 1, right? That's important. Only when it's set equal to 1 do I get to look at these denominators and say, oh, there's the value of A, you know, that's A squared and that's B squared as we realize them as coordinates on the graph. And I bring that up because in our next example, they give us another equation, and they want vertices, ends of the minor, and the foci. They didn't ask us to sketch this one, but I'm looking at this, and I'll tell you, I can tell it's an ellipse. And the way I can tell it's an ellipse is that it has both an x squared and a y squared, but the coefficients are different, but both the same sign. So they're both positive, but they're not the same. If they were the same coefficient, what would we have? That'd be a circle. Yep. So we want to kind of do a similar thing with this equation as we did the last one, but we just have to start by getting it in standard form. And if I want this to be equal to 1, the useful way to get it to be set equal to 1, I mean, I'll tell you, here's not a useful way to have it set equal to 1. Be like, oh, I'll just subtract 63 from both sides. It would be set equal to 1, but then it still would not be in standard form. So instead of doing that, we'll just divide both sides by 64. Four goes into 64 16 times. 16 goes into 64 4 times. Now that's in standard form. Which way is it oriented? Yeah, right, the big number's under the x, so we know that a squared is equal to 16, which means a is 4. So the vertices are 4, 0, and negative 4, 0. B squared is equal to 4, so b is equal to 2. And that means that the ends of the minor are at 0, 2, and 0, negative 2. And now we need the foci. So let's use that equation again. B squared plus c squared is equal to a squared. So c squared is a squared minus b squared, which is 16 minus 4, 12. So c is root 12, or root 12 is 2 root 3. Right, take out that 2 times 2 times 3, so we take out a pair of 2's, become a single 2 outside. And what are the coordinates of the foci? Like, if I were to write down, here are my foci.
2, 3, 0.
Mm-hmm.
Negative 2, 3.
Yeah. The orientation of the ellipse is important for figuring out what your coordinates are. Like, okay, obviously it's 2 or 3 is going to be important, but like, oh, is it the x coordinate or is it the y coordinate? Because it's oriented horizontally, I know it's the x coordinate. How we doing? Let's do another one. They want us to find the equation of an ellipse center at the origin and one end of the minor axis, excuse me, at 2, 0, and then it passes through the point 1 root 6. Okay, the center is at the origin, so that tells us something. We know kind of the basic form of the equation that it's going to have. But this problem is different than the other ones. The other two problems that we just did, they gave us an equation and asked for some information about the curve. Here they're giving us information about this curve and they want us to get the equation. Those are the kind of the two varieties of problems that we tend to solve in this chapter. When they tell us that one end of the minor axis is at 2, 0.
Vertical.
Yeah, it's going to be oriented vertically because the end of the minor is on the x-axis. Yep. And then they say it goes through the point 1 root 6. So root 6 is 2 point something. So maybe like that's a point on the ellipse. There's my sketch. Perfect. I know that it's oriented vertically, so how do we use that? Like, we know it's oriented vertically. What does that mean about our equation?
That means that we can pretty much figure it out because x is 2, so x squared would be 4.
Oh, A, you mean, sorry, end of the minor. So I think that's B,
Or it would be B.
right?
Okay.
So like, they're telling, with the end of the minor is, so since it's centered at the origin,
Just work backwards, though, right?
yeah, like, so they told us here that B is equal to 2. But also, what's the basic form of the equation we're going to start with?
Y squared over A
Right.
squared
Yep.
r plus x squared.
Yeah, so can't you just plug in the coordinates at that point for x squared and y squared?
Perfect. That's exactly what we can do. So we know that B is 2. I'm going to go ahead and throw that in first. So y squared over a squared plus x squared over 4 is equal to 1. And yeah, that's exactly what, the only thing we need in order to solve this, we need to figure out what a squared is. Aaron pointed out that we have a point. When we know a point that's on the curve, we're allowed to substitute those values in for x and y. That is like almost like the first commandment of analytic geometry. Is like, if you know the coordinates of a point on the curve, remember that that means we're allowed to plug those in for x and y. So let's do it. So root 6 squared over a squared plus 1 squared over 4 is equal to 1. So a couple ways we could go about this algebraically, but maybe I'll just subtract a quarter from each side first. And so we get 6 over a squared is equal to 3/4. And I'm going to clear denominators now, so I'll multiply both sides by 4a squared. So we get 24 is equal to 3a squared, which means that a squared is equal to 8. And that's pretty much, we're just about done, right? So that's all we needed to finish finding this equation. So we have y squared over 8 plus x squared over 4 equals 1. How's that? Now, what if our, there's a bunch of ellipses that are not centered at the origin, right? Like, there's nothing special, I guess, about the origin. We could center our ellipse anywhere. It still has the same basic structure to the equation. We're just going to replace x with x minus h and y with y minus k if the center is at hk, just like we do with a circle, right? Just like we do with the parabola, for the vertex of the parabola. So let's do another one. We're gonna sketch this curve. They didn't ask us to find any particular information about it, but if I'm gonna sketch an ellipse, I usually make sure I have the vertices and the ends of the minor, and then I can, that's usually enough for me to get a sketch. So what do we know about this ellipse? It's oriented horizontally, yep. What else?
A squared equals
Say that again?
25. A squared equals 25.
Mm-hmm.
B squared equals 9.
Yeah. So we know A is 5. We know B is 3. What else do we know?
Its vertex is at 3, -2.
Yeah, the vertex is at 3 negative, or the center
Yes.
is at 3 -2.
Yeah, the foci is 4 because it's a 3, 5, 4 curve.
Uh-huh. So I'm not going to say the foci is 4. You're right that C is going to be equal to 4, right? Do we know the vertex? Do we know either of the vertices or the ends of the minor? I mean, we found A and B.
We can.
What?
We can.
We can, right? So let's start sketching. I'm just going to plot
We know
the,
that one, like, is gonna be 4.
oh, it's 3, -2. Somebody said that, and I just omitted the sign. Sorry, keep going.
I'm sorry.
I think I interrupted you. I thought I interrupted you. I think you were talking about how we would get the vertices, maybe, or the ends of the minor, or maybe you weren't.
Well, they're on a horizontal plane to the center, right?
Yeah.
So it would just be 5, -2, and -5, -2.
Why 5?
Because it's horizontal and A is equivalent.
So 5, -2, like that. So there's a vertex, and
I think
then
you're thinking 4, because you're thinking of 3, 4, 5, but one was very close.
so like that.
4.
So you're saying the center's here?
Oh, sorry. I spaced. Never mind. You have to do 5, the distance equation.
Yeah, it doesn't have to be the distance equation, but like
Yeah.
A is only the actual coordinates. A and B and C are only the actual coordinates when our center is at the origin. If our center is anywhere else, A, B, and C gives you the distance to each vertex, or the ends of the minor, or the foci. So, in fact, what we're going to do is go 1, 2, 3, 4, 5. So that's over here at 8, -2. And then 1, 2, 3, 4, 5 here at -2, -2. So, yeah, 8, -2, -2, -2. And that's because we're going 5 units in either direction. What about the ends of the minor?
It's gonna be 3, 1, and then 3, -5. You just add
Yeah.
both sides, or add
So-
-3 rather.
Yep, so we're going to go up 3 and down 3 from the center. So we're going to add and subtract 3 from the y coordinate of the center. So that's going to put us up here, as you said, at 3, 1. And -5, 1. Oh, wait. 3, 1, yep. And then 3, -5. There we go. Much better. And now we have, I think, enough information to get a decent sketch. So, the reason we call it standard form is because I know where it is, and then I can find the ends of the minor and the vertices pretty quickly, and kind of look at that equation and get it almost immediately, kind of an idea of like where it is. What does this ellipse look like? You want to do another? Might as well. If you thought, so I know what you're thinking. All this time, you're thinking, how have we gone this long? Like, are we not going to complete the square in this section? I have good news for you. We're going to complete the square. Why do I need to complete the square? Like, why do I look at this and I say, I'm going to need to complete the square?
Standard form.
It's
good standard form.
We want it in standard form, right? So I look at this equation. How do I know it's an ellipse? Like, outside of the fact that it's in this section on ellipses, like, how do I know it's an ellipse?
They have different coefficients.
What?
Coefficients different. Squared with different coefficients.
Yeah, but the same sign. If they were different coefficients with different signs, like if one was plus and one was negative, you actually get a hyperbola. You get which is not a slightly different, a very different figure. And yeah, it's definitely not in standard form.
What do
Yeah.
you mean if it was 2x squared minus y squared?
Mm-hmm. Yep.
What if it was -2x squared minus y squared?
Well,
Then it would be an ellipse again, because they'd have the same sign.
Oh.
Yep.
Duh.
Yep. So we're going to complete the square. And just like we do with the circle, I'm going to gather my x's with the x squared and then my y's with the y squared. We have to be a little bit careful because these coefficients are not the same. And just like with a circle and just like with a parabola, we want to complete the square on x squared, not 2x squared. But I can't divide both sides by 2 now because that'll mess up the y squared, right? So what we need to do, let me rearrange this first, plus 8x plus y squared minus 8y. If there were a constant term over here, I'd make sure that was over by itself. Our constant term is just 0. So what I need to do is instead of dividing by 2, I'm going to factor out a 2, but just from the first 2 terms. So I'm going to have 2 and then parentheses x squared plus 4x. I'm leaving some space in the parentheses because that's where I'm going to complete the square. And then y squared minus 8y. Leaving some space. What do I need in order to complete the square on x?
2 squared.
So I'm going to add 2 squared. Now, this is really important. Just like we did, when we're doing the circle, the parabola, I added this, I need to add it to the other side. But this 2 squared is trapped inside a set of parentheses as being multiplied by 2. We didn't actually just add 2 squared to this equation, to this side. We added 2 times 2 squared. So when I do the same thing over there, I need to make sure that I also,
So plus 8.
yeah.
Okay, I see what you mean.
And that's only because you took out the 2.
Mm-hmm.
So you have to take it.
Yeah, like if I distributed this 2 right now, right, I would see that I've actually added 2 squared times 2. Right, I will have added 8 to that side. So I'm just making sure I do the same thing over there. What do we need to complete the square on y?
Negative 4 squared.
Mm-hmm. So now we have, I got to bring this 2 down with us, don't forget it, x plus 2 squared plus y minus 4 squared, and then 16 plus 8 is 24. So we have completed the square. Is it in standard form? What do we need to do now? What?
I was going to say put it to 0.
Say that again? Divide by 24. It needs to be set equal to 1.
Yeah.
Yep. So we have x plus 2 squared over 12 plus y minus 4 squared over 24 equals 1. There it is in standard form. Now we're supposed to find all this information. What's the center? Close?
Negative 2, 4.
Yeah, negative 2, 4. And then we want vertices and foci and then sketch, which means we also really want ends of the minor too, right? So which way is this oriented? Vertical, yeah. So a squared is 24, which means a is the square root of 24, which is 2 root 6. Or, you know what, we're going to sketch this, which means I'm going to try to plot these points. I'm going to go ahead and just approximate that. .89. I'm going to call it about 4.9. I mean, I'm sketching, so like I know I'm not going to get my sketch any more accurate than the 10th place. So, and then b squared is 12. So b is root 12 or 2 root 3, and that is 3.46. I'll call that about 3.5. And then what about my ends of the minor? Oh no, that's ends of the minor. What about my foci? How do I find it?
Oh, it's the Pythagorean theorem.
Yeah, right. So that relationship that we derived, that's b squared plus c squared equals a squared. So c squared is a squared minus b squared, which is 12.
Yeah.
So c is root 12, which is going to be about 3.5 again. And I wrote that as, we haven't found the foci yet. We just found the value of c, right? So a, b, and c just give us distance from the center. So our vertices. This is oriented vertically, we said, right? So what I'm going to do is I'm going to take negative 2, 4, and since it's oriented vertically, I'm going to add and subtract 4.9 from the y coordinate. Negative 2 minus 0.9 and negative 2, 8.9. The ends of the minor. I'm going to start with the at the center and add and subtract the value of b from the x coordinate. So that's negative 2 plus or minus 3.5. And then the y coordinate is going to be 4. So negative 5.5, 4, and 1.5, 4. And then foci are always on the same axis. They're on the major axis along with the vertices. So I'm going to take negative 2. That coordinate will stay the same. I'm going to add and subtract 3.5 from 4. And then they asked us to sketch it, so my apologies. I didn't provide probably enough space. No fair that I have extra magic paper on OneNote, but we'll make it work. So the vertices, negative 2 is negative 0.9. So like right there, and then, whoops. So, and then 8.9, so very close to 9. And then the ends of the minor, or the center was at negative 2, 4. There's the center. And then the ends of the minor, negative 5.5, 4, and then 1.5. And then we get this. It looks kind of like a lot like a circle when I drew it because my scale is a little bit, my y, the scale of my y is not the same as the scale of my x, so it looks a little bit more circular. How's that?